Every time I find myself speaking, I'm reminded that the world has not yet built a podium for those of us that have extreme verticality. But anyway, here we are. I'll do my best, and my back will hopefully hold out. At this time, it's my pleasure to welcome Carey Priebe to the stage. Carey joins us from Johns Hopkins, where he's a professor of applied mathematics and statistics. He's also the founder of Johns Hopkins Center for Imaging Science and the Mathematical Institute of Data Science. Please help me in welcoming Carey to Philadelphia this morning. Carey.
Thank you, sir.
Right there. Good to see you. Thank you.
Thank you. I appreciate the invitation, and I'm looking forward to my talk. I don't know if you will be, but that's fine. So the title is Discovering Dynamics in Network Time Series. So I think that most of us will be able to see that we might want to do that. Network time series are all over, and principled methods for discovering understanding structure in such a time series of graphs, time series of networks are few and far between. There's lots of ad hoc methods, and I sort of made my career on doing what I call principled ad hoc. That is, I don't just make something up. I try to figure out what it is that I would do if I could, and then not do that, and instead do something that I can. And so that's what I'm going to show you, something that I can do. And the core example I'm going to use is not from finance or anything else. It's from neuroscience. And so in neuroscience, we have these new things called brain organoids, brains in a dish, however you want to talk about it, but they're cerebral lumps of neurons that they grow in the dish for all sorts of wonderful reasons. The photo is my colleague at the University of California, San Diego. His particular interest is autism, so they're trying to understand diseases or whatever. But we have the organisms, or organoids. So we'll get back to this example at the end. But the x-axis is time. So this organoid grows for some number of months. And the y-axis is something that I'm not going to tell you right now. You don't have any idea what it is. At the end of the talk, I suspect most of you won't have any idea what it is, but you'll know who you could ask. But it's this thing that I call the isomirror. And it basically is capturing the dynamic structure of the time series of networks. So the time series of networks is a very complicated object. The data point, the data I have is a time series of networks. How do you get that into a one-dimensional curve? It's a long story and ugly, I have to say. But the idea is that there it is. And just a nice picture, because I believe even the non-statisticians in the audience can see that there's a change point in this time series of networks. At about day 160, there's something that's changed. And my wonderful graduate student, Tinyi Chen, did this. He's here in the audience. And when we showed this to the neuroscientists, they looked at it and they said, oh, yes, there's the particularly most interesting thing from these organoids happens at about that time. That's not causation, but it's correlated with something that they care about. And that makes me happy. So I'm going to try to explain where that figure might come from. I'm not going to give this data, but this is a teaser for, say, Chris Harvey or whoever, with a couple of my very incredible young colleagues at business schools. This is the only business school relationships I have, are these two plus Edo. But we're considering a time series of intercorporation competition networks derived from various data, and the idea would be to show you a figure like the organoid figure on this data. I'm not going to do that today, but it's a teaser of what I'd like to do at some point. And so hopefully this will convince you, this figure will convince you that there was one slide that was worth your time this morning. So the idea is I have a collection of actors. They could be corporations, they could be neurons, they could be individuals in an email network. But at each time, I have the collection of actors, and I have interactions between them. And this figure, this cartoon, is specifically designed to give you a couple of points. First of all, these are complex networks. That is, each of the nodes, each of the actors, has a color associated with it here. So, different corporations might have different attributes, and so it's not just a simple graph like you might find in raw academia. And the edges themselves, they have colors associated with them. That is, you might have some interactions that are email and some interactions that are in person. That's an old thing that the kids today don't know about, but there used to be an in-person thing that we would do. And so at each point in time, you have such a network. And then the question is there a time t star at which the structure of the network changes? And so in this particular case, the cartoon is designed to give you the idea that at time t star, one group breaks off and starts behaving a little bit differently than it did in the past, while the major collection of actors continues in the same vein that it was beforehand. And then there's two types of statistical inference problems that we can consider for data like this. One is a change point, which is depicted here. So at time t star, there's this change, and this is supposed to show that at time t star plus 1, that change persists, and it continues. So t star is a change point. Another is an anomaly, and these are pretty close to, this is my definitions, it's pretty close to pseudo-standard. But an anomaly would be where there is this change at t star, but then at t star plus 1, it goes back to the way it was prior to t star. So it's not persistent. The change doesn't persist. And so there's two different problems, and from a statistical point of view, we address them differently, but from the cartoon point of view, that's what we have. And so the idea is that at time, we estimate t star here to be 160, and something changed in the network, and what the y-axis that you don't know about demonstrates is that we have this change point. So that's the story. Okay, this slide is designed to show you that you've had enough. You've already seen everything you want to do, and you could go get coffee. But here's the kind of theorem that I would like to prove, actually Tinyi proved. And it's just, I'm putting it up here to give you a hint. So we assume some stuff. And that's all I have to say here. And then we consider a time series of networks. We have n vertices. In order to do mathematical statistics on such an object, we have to assume a distribution or a model, a collection of possible distributions. And that's what this says. It says governed by some process. And so if I have a collection of scalars, I might assume I have a Gaussian and wonder what the mean and variance are. If I have a time series of networks, an analogy to assume a Gaussian with unknown mean and variance is assume some process that governs the evolution of the time series of networks. Who interacts with whom? Which vertices interact with which vertices? And that's a very long story, but I have to make some assumption like that. And so then we assume that we have some unknown t star, a change point in this underlying process that governs the dynamics of the network. We have a procedure for estimating t star that gives us an estimated change point t hat. Lots of ways you could do that. That's just statistics. And we're able to prove that t hat minus t star is small. And that would be what a statistician would do, and that's what we're able to do for this problem, and that's all you need to hear from me for today. I won't prove that theorem today, and this will show you that some of you care desperately to know what theorem X and theorem Y would be that would prove such a theorem, and some of you care less desperately. But in any event, the idea we want is that the true but unknown T star is close to the estimated T hat, and if we can prove that, then we could say there really is some change in the underlying dynamics of this brane organoid near time 160. And that's the story. Okay, so as I said, Tin-Yi Chen is in the audience. He's a graduate student that you want to hire, but I'm going to insist that he never graduate and just stay with me because he's useful. And the brains behind the other operation are Avanti Athreya at Hopkins, Zach Luberts, who's just moved to University of Virginia, and Youngzer Pike Park, my longtime right-hand man. So if you want to talk about this, I'm here all day. The story is I have to estimate this isomirror, the y-axis on my brane organoid change point detection slide. And we're going to get to some idea of what that is, but the algorithm for estimating it is at the top there. First, I tape my time series of graphs, and I do the only thing I know how to do, eigenvalues and eigenvectors. I do a spectral embedding of each graph in the time series, and so now I have Euclidean data, a time series of matrices with just numbers in them, and I'm better off. So this spectral embedding step gets me to a point where I can do something. Then I have to get a norm between, a distance between the network at time t and the network at time t prime. So I want a distance between networks. But once I've done this spectral embedding, I can ask for a distance between these matrices, these n by d matrices, if I have n vertices, and I have lots of opportunity to develop distances between matrices, and we've picked one for two reasons. One is that it works in practice, and the second is that we can do math on it. And some of them that work better in practice, we have more difficult doing math on, et cetera, et cetera. You know the drill, but we have versions that kind of work and we can really do math. We have versions that really work and we can kind of do math. And my proposal is to, depending on the actual application, whether it be email networks across time, organoid networks across time, or the thing I care most about, Wells Fargo networks across time. Presumably there would be slight differences in the algorithms that would work, and so we'll worry about that when the time comes. So there's a lot of papers out of my group over the last decade and from lots of other people about spectral embeddings and distances between them, and suffice it to say that I think this is all principled. That is, the theorems hold, and some journal or another has a referee who's checked the proofs, maybe, if you know about refereeing these days. But we have this algorithm then across the top, spectral embeddings, pairwise norms, then this CMDS, that's multidimensional scaling, that gives me a dimension reduction because the pairwise norm on the networks, if I have time t equals 1, 2, 3, all the way to 1,000, or whatever it was in the organoids, maybe 300, I have a 300 by 300 matrix then. The distance, the ijth entry is the distance between network I and network J seen through this spectral prism. What do I do with that matrix of distances? Well, multidimensional scaling gives me a representation in low dimensional space where the Euclidean distance between the points in this low dimensional representation approximate the distances in this T by T matrix. And then we do this isomap to get the iso mirror that I've described, and now you know all about the iso mirror. But that's the end of that algorithm is our iso mirror. Well, that was unpleasant, right? So let's do something equally unpleasant, but from a completely different direction. Overly simple. So I have a network, and it's governed by a process phi, and that's the latent positions of the network. So there's an entire body of work on networks governed by latent position models. And that is, each individual vertex has a point in some space, and the relationship between those points gives rise to the probability that those two vertices have a connection. So I like sports and math, Edo likes beer and math. We have some similarities in our latent space, so we talk sometimes, but he doesn't like sports and I don't like beer. So we don't talk as much as we might otherwise. Well, the simplest such latent position would be just scalars here. So this is called the London model because Tinney and I came up with this while we were in London. It's the only reason. Hopefully the next talk I give will have the Philadelphia model. But we're stuck with the London model for now. So the idea is that the latent position process evolves as that. That is, it just jumps with probability. And so I get this xt, and then I draw a random variable from the distribution to get this random dot product graph. We understand the mathematics of it entirely, and it turns out to fit into a dynamic stochastic block model, which if you do networks, you know too much about. And if you don't do networks, let's just say it's the simplest thing that academics came up with a long time ago to study networks. And the idea is that for the ith vertex at time t, I have a latent position given by the process that I just presented. And at time t, all n latent positions are independent and identically distributed. So that's pretty simple, maybe unrealistic, but if you try to do math, that's going to be a reasonable assumption. But the model is not too simple to be interesting because we have this dependence structure. And dependence is a terrible thing. Turns out reality has dependence, but Timothy Leary said reality is for people who can't handle drugs. Nonetheless, in order to have the model be relevant to any real data, we have to have dependence. And so the idea is that for a given vertex, for Alan Carr, vertex I, as time goes from 1 to m, we have this dependence structure. That curve, that latent process associated with Alan Carr, is governed by a joint distribution, not just a marginal. And then Edo gets his own process, which has the dependence structure. So the dependence is governed by this dynamics in the latent space. Okay, so a bunch of words that kind of say what I just said. The trajectories are an IID sample from the latent process, and so we can study the dependence across time, but we can study just the distance function on the latent position process at xt versus xt prime. And so we can get our hands on how this network is evolving based on the model that we've just described. And we've come up with a distance that depends on more than just the marginal distributions, but takes into account their dependence inherited from the latent process. So that's a bunch of stuff, but remember what our goal is. I don't know what your goal is, actually. I can't say. But my goal was to take this just time series observed networks, come up with a model that I could care about, and have an algorithm that estimates a change point, that is, gives me t hat, that I can guarantee is close to a true t star if there is a change in the dynamics. And the model that I've described here, poorly, is a model for which we can prove that a t hat obtained by a particular algorithm will be a real change point, and you'll be able to say, yes, today the model governing the process, the time series of networks, has changed from what it was yesterday. So a little bit of math, but I want just the red picture. So for this model, and notice there's no change point in this model. Let's look ahead. It turns out that we can do all the math on this, and we get the distance squared between time t and time t prime is given by that simple expression right there. And here, I hope p is some probability in the model. We've got a t minus t prime, how far they are away from each other. If you've done time series analysis, and most of you have, we've boiled this down so it looks like something we might otherwise have considered. And so, nice simple expression. You're not supposed to internalize much, but try to remember how simple that expression was. Well, the question is, does this image, this is the thing that I'm calling the distance between the latent position process at time t and at time t prime, does the image of phi, when seen through that metric d that I had on the previous slide, does it capture anything that I care about? And that's where this mirror comes from. It turns out that Avanti and Zach, the brains behind the operation, proved that if I have a model like I'm talking about, a time series of networks, a dynamic networks with simple enough structure, then there will be this thing called the mirror, which is a one-dimensional curve in the simplification I'm talking. A one-dimensional curve winding through low-dimensional, d-dimensional Euclidean space, and that curve is capturing the dynamics of the time series of networks, the dynamics of the stochastic process. So the mirror is the thing. By the way, some of us are old enough to know the name Alfred Hitchcock, but that's a picture of Alfred Hitchcock in front of a funhouse mirror. It's there because the idea is that the mirrors, funhouse mirrors, distort things. I'm not magic. I'm clever, but I'm not magic. I'm clearly not going to be able to reduce a dynamic network into a one-dimensional curve without simplifying some things and missing some things. So the question isn't whether I completely faithfully retain all the information. It's whether I capture some useful information in the distortion that I'm employing. And the answer is yes, and this is the idea. And so the story is that these are just definitions of what it means for the process to be approximately Euclidean realizable. And the idea is that the process, if there is a curve, a one-dimensional curve, psi, in this low-dimensional space, c-dimensional space RC, if there is a curve such that the psi's look pretty close to the distances, the pairwise distances, then I have captured something useful. And so the question, we've got a formal question, when does a dynamic network exhibit such a realizable structure? And now you desperately want to hear the rest of the talk because you wonder, when does that happen? Somebody must wonder that. So this again is our simple little model, and what Tinyi has done here is he's come up with the psi, or an approximation to the psi that is associated with this London model, and it might look ugly to begin, but then you see it's alternating sines and cosines, and you understand that you did do this as an undergraduate. You probably didn't enjoy it, but you did do it. And so we can prove that in this particular case, we do have this asymptotic exactly one realizable for this very simple London model that I don't think you should care about. That's to show you that I have at least the stage presence to skip that slide. But what I have here is just a little bit of plotting. Remember, this one-dimensional curve winds through low-dimensional, c-dimensional space. And so I can look at each of those 3 dimensions. And all I want to show you here is that I have 3 colors, black, red, and blue. And the black is exact, and the red is the theoretical approximation, and they're right on top of each other. They're not perfectly on top of each other, because the approximation is an approximation, but it's really good. And then the blue is what happens if I actually realize this from a time series of 400 networks, each on 1,500 vertices, and the blue looks just like it's trying to be the black and the red. So that's great. Who cares? I do. Here's from this Euclidean Mirrors paper that Avanti and Zach came up with. The story that I've been saying is on the right is the true stuff, that is the assumed model, and there is this latent position process phi and the x's, and I get this distance between the x's. I get a one-dimensional curve in c-dimensional space. And on the left is that algorithm I talked about at the very beginning. You do spectral embedding of each network, and you come up with a distance between the matrices, et cetera, et cetera. And just look at the 2 arrows going from left to right. The theorems show that the things on the left, what I do on the computer in practice with real data under our assumptions, does indeed converge to the math story that I'm telling. So that was boring, but presented well. So let's do something let's get to a little bit more interesting. It's never going to be Wells Fargo time series. I mean, I got 18 minutes left, and I'm not going to get there. But at least here, I have this really low-dimensional London model process with a change point. So in this particular case, up until t star, I have a particular dynamics on the latent process. And then after t star, I have different dynamics on the latent process. So this is the simplest model we could come up with, which gives us a story where we could hope to estimate t star. And I wonder what's on the next slide is that distance in this new model between time t and time t prime. And I asked you to remember that red slide before. When there was no change point, that distance was really simple. When there's a change point, it's significantly more complicated. The distance depends on whether t and t prime are both before the change point, both after the change point, or one of them is before the change point and one is after. That should make sense. This distance matrix that I'm talking about, remember I get my data, my time series of networks, I do some things, and I end up with a distance matrix, that is the distance between the graph at time t and the graph at time t prime. Well, it should be the case that if the process is stationary up until some t star, and then stationary after some t star, that distance matrix should have a block structure. The distance between all the matrices before t star should be, that's what this shows. So, turns out not to be particularly complicated once you break it into those 3 pieces, and so we can fully understand for this model what does this distance function look like between the processes at these various times. Won't worry about that too much anymore, just go to the picture. Tinyi, when they teach you how to give a talk, go to the picture. Just go to the picture. So here's the London model with the change point, and again we have black, which is this exact calculation via CMDS. We have the red, which is no longer the theoretical approximation, now it's the limit, the limiting object. And again, black and red are right on top of each other. And again, the blue, the estimation from an actual realized time series of networks, looks like it's trying to be there. But now we have something at least as interesting to look at. In fact, it looks a lot like it was designed to look a lot like the organoid example. On the y-axis is kind of the isomirror for each of the first 3 possible dimensions. And we see that we can see the change point in that first dimension. So the algorithm that we're talking about sees this change point. And it's just like the change point it saw in real and horribly complicated organoid neuroscience data. In this case, we know exactly the model. We can see that it's getting the right answer. The question is, can we prove that that T hat looks like T star in general? The answer is yes, and I told you there's a theorem X and a theorem Y that I'm not going to tell you that proves that. So here we can do it. We've set it up, but the same story says that under appropriate assumptions, that's what we saw in the organoid model. So this is as it should be, and I do kind of like this. Let's do Monte Carlo since we can actually draw as many time series of networks as we want from this simple model. And this is just to show you that there's two things going on, and if you had looked at the upper bound on T hat minus T star, the absolute value of T hat minus T star on my original theorem slide, the one where you checked out and started doing real work, you'll notice that the upper bound has two things in it. It has n, so on the left panel, what's increasing is n, the number of vertices in each network. So if I have a network of 100 companies across time, a time series of networks where each network has 100 companies versus a bigger one where each network has 1,000 companies, et cetera, I would expect to be able to estimate the change point better with more vertices, and that's what I see. The mean squared error of the change point estimator T hat goes down as the number of vertices increases. But also, if I have a fixed number of vertices in my networks, but I get more and more networks, and this is what's called infill asymptotics, as opposed to, time goes out, but here I'm getting finer and finer observation of the networks. I also ought to be able to estimate my change point better. And so for the right-hand side says for fixed n and an increasing m, I also get an improvement in the change point estimation. So I will have told my students and postdocs that if they have a theorem and they can't generate a Monte Carlo simulation that at least doesn't contradict their theorem, they should do so. They should also work on real data. My advisor a long time ago told me that any good paper has three things. It has theory, it has simulations, and it has real data. They all serve different purposes. So you've seen all three of those, so you can think this wasn't a total waste. Well, how does the theorem go? I'm not going to tell you too much about it other than the isomirror is this one-dimensional estimate, and the idea is, again, as an undergraduate, you knew that if you were doing regression, if you had yt and you assumed that it looked like some f of t plus noise epsilon t, you would know how to do this problem. And we do. We have this mirror psi hat that's playing the role of y. And Avanti and Zach proved that there is a true psi that this psi hat is estimating. And so we have exactly that. And our psi in this simple model is just piecewise linear. It's got a single change point. This is like high school. Not high school when I was in high school, but maybe now. The problem is when you do this problem, you know something about the error distribution epsilon, and we don't know very much about the error distribution epsilon hat, at least not the kind of things we'd need to know in order for you to apply the perfectly good theory and methods that you're aware of. It turns out that theorem X says right there that we can say something like, so this psi hat in the middle of the screen has a tilde over it. I'm not going to tell you about the tilde. I mean, you didn't care about psi. You sure as heck didn't care about psi hat. And if I'm going to put a tilde on it, I mean, that's just silly. And it is. But the idea is we can prove that it's not very far from that psi. So we can at least prove that these epsilons are small if n and m are big. And that right-hand side, how small is it? It's got to do with spectral decompositions and things like that. And then lemma y just says that we can prove that however we estimated psi with psi hat, the change point estimator, t hat, would be as close to t star as something to do with how good psi is, how close psi is to psi hat. So the idea is you knew a whole bunch about epsilon when you did your first linear regression. But in order to prove that the change point estimate converges to the truth, all you really would have needed to know was that the psi hats are small and they get smaller as we go along, as something goes to infinity. And that's what we have for this particular case. So our algorithm for estimating this mirror, this isomirror, is quite complicated, but we can prove the simplest things we would need in order to do rigorous principled statistical inference to identify the change point. And let me skip this, but if you've seen me talk before, you know that I think all problems come down to the bias variance trade-off. That is, when I'm making an assumption, a model assumption, I can either make it complicated, in which case it's possibly closer to reality, but I have more variance because I have more things to estimate, or I can make the model simple, in which case I can estimate everything really well, but it's not close to reality. And if you don't have a bias variance trade-off, you probably are missing something in your approach. I have a bias variance trade-off here. Okay, so I'm about done. If you recall, the algorithm was turtles all the way down, a bunch. I only know one thing, which is how to do an eigendecomposition. And so each of these steps has an eigendecomposition in it. And if I get a new student and we upgrade this algorithm, we'll just throw in more eigendecompositions because nothing can go wrong, right? But we all know that the model that I've assumed for Chris Harvey's Wells Fargo time series of networks, or for the organoid, it's not right. It's wrong. So the question is it close enough to right to be useful? Another way to say it is Walter Shewhart, who hopefully you learned about in school, invented the control charts probably 100 years ago, maybe 100 years ago this year, possibly 1920s. Anyway, he said all the highbrow statistical theorems in the world doesn't make your procedure work on real data. You should check. Probably a good idea. The great American sage Yogi Berra didn't say it this way. In practice, there's a difference. So for the brain organoids, this is the team that put together UC San Diego, Microsoft Research, and then Hopkins and whatnot. Oh, and Tiny's paper on applying this stuff to the organoids has been accepted or appeared in that journal right there just this year. My time is up and it's time for questions, but I do want to say two things about this. First of all, where does the network come from? That's all I have to say. That is, when you're thinking about doing a problem like this, complex data, it doesn't get much more complex than a time series of networks with attributes on vertices and attributes on edges and everything else. Well, if it's companies and how they communicate with each other, how they relate to each other, I mean, there's a bunch of sausage making that goes into putting that time series of networks on Carey's computer. Similarly, for the organoids, Francesca and her colleagues from UCSD, they did a bunch of terrible signal processing, and there's bloody actually neurons in a dish. So, I mean, it gets pretty ugly, right? So who knows what's really going on behind the scenes, and that sausage making we really have to kind of understand Let me skip that. This is a, yeah, skip that. No, let me go back to that. But the second point that I want to make is that all of the theory that I told you I had, but it's in my back pocket and I won't show you, that we've described so far is for a situation where you know which vertex at time t is which vertex at time t prime. That is, if it's companies, you know which company across time. If it's individuals, I know that this email account is Edo throughout the entire time series. But there are problems, the organoid is one, where you don't know that. There are neuroscience applications where you know the neurons, which neuron is associated with which neuron across time, but this isn't one of them. In the Microsoft email, we had that, and this was just to show that I do have the temporal vertex correspondence, and what I found was a change point in spring or early summer of 2020, which was right when COVID hit, right when the work from home order came. So this is like 100,000 actors across 24 months of Microsoft email, US Microsoft email. And we find a change point coincident with COVID. I can't say causal. Some of my colleagues will say that later. But we find that. But in this particular case, we have the one-to-one correspondence across time. If you don't have that one-to-one correspondence across time, then you can't apply the theory that we just have. But I have for the last decade, a whole second area of research, which is graph matching. I have two networks and two possibilities. One is I assume there's a one-to-one correspondence, and I ask, can I recover it? And the other version of it is, there is no one-to-one correspondence, but I still want to find the best match. And there's a lot of beautiful papers. This work, a lot of it's led by my former student, Vince Lazinski, who's at Maryland College Park now. But if you have a problem where you have two networks or multiple networks and you don't have a vertex alignment, there's a lot of good stuff that we can do. And so we have to do that for the organoid, and I just wanted to say that. And so the last slide, I didn't tell you something that you would have needed to make sense of this, and my time is up, so let me jump to the final slide I have, which I think is important. So I want to do math. I want to prove theorems about an estimator t hat and its relation to t star. And I even want to do it with time series of networks. I could just do that in a vacuum for that kind of problem and write good papers and maybe even have stuff. But there's real data out there. You have real data in this industry, the neuroscientists. There are applications. Why not work on their problems where you have a direction given to you by practical experience with real problems? And that is a secret weapon even when you're just trying to do theory and methods. It's a secret weapon because you can convince yourself that the model you've just described is a good model, but if you can't find any data, no matter how many friends you have, that make sense for that model, maybe you should have picked a different model. Still have to pick one that, my model is still silly because I have to be able to do math, but at least it's silly, but the direction was given by real data. And so I thank you for your time, and I apologize. I'll try to do better next time. You said you would not heckle me today.
No heckling. Fantastic talk. This is very, very interesting. And when you were talking about the epsilon and what is that, it got me thinking, in change point problems, you're trying to distinguish between, is it just a random blip or did something big happen? So how do I think about the signal to noise ratio in your context?
Good. So thank you, Ed. That was actually not as nasty as it could have been, right?
Later.
So I don't know, can anybody repeat his question? All I heard was fantastic talk, wonderful work. I think he said something after that, but I don't know. So, so if Tinney had come to me with a blue vertical line, or whatever color it is, for this being the change point, and he probably did, I would say, we're statisticians. If you don't give me a confidence interval, you'll never graduate. So the blue shaded lines are confidence intervals. And so we do have, obviously, we have to have some idea of the signal to noise ratio and whatnot in order to get confidence intervals. And the two different pictures here, the point was that the one on the right has a smaller confidence interval than the one on the left. And that's based on something fun. But let's see if I think I have a slide that's not unrelated to your question. But Yogi Berra, well, who wants to hear about the answer to Ed's question, and who wants to read Yogi Berra's quote? I mean, seriously. Even if we're Yankee haters. So the signal to noise ratio on the stochastic process itself governs everything else in this simple model. It's just a change point model, and you've got a stochastic process. And so the right-hand side of this estimate, so this is looking at it through the mirror psi and the estimate psi hat, but we can see that, I mean, essentially I'm going to interpret your question, Ed, as what's that on the right-hand side? And so I have M, which is the number of graphs. And again, infill asymptotics is tricky. I always want to caution you on that. And N is the number of vertices, but the PD squared P, that's the spectral properties of, it's essentially the spectral properties of the latent position model. So if the latent position model is really low dimensional, then when the number of vertices is big enough, you'll focus right in that. And so this all stems from the great and wonderful Min Tang, who was my postdoc years ago and is at North Carolina State now. But basically, his work, along with Avanti and Daniel Sussman and myriad others, was to show the simplest, Ed, is to derive a central limit theorem for the eigenvectors of the SVD, if you will. And so the latent position process is really governed by this low dimensional thing, but for a finite n, I don't have that low dimensional structure. If I knew the distribution of the eigenvectors, I could do it, and I don't know, but Min knows. But that's where it comes from. All the signal to noise properties come from that.
Okay, so I have a follow-up question. So first of all, I want to say, great talk.
And how about the eigenturtles, huh?
Turtles, amazing. This, I remember when you wrote this, I think it was an Amstrad News article where you laid, this research agenda, and you've come a long way.
That was 100 years ago.
I know. That's how old we are. So if you fix the dimension, I have a similar question. If you go back to the Monte Carlo slide, so if you fix the latent space dimension, do you get more bang for buck by collecting, more time points, or by having a larger network, I guess?
Right.
Which one?
Right. So if the latent space is fixed,
right,
always. Actually, I should take that back.
If
there is, you're right. I should, especially if I'm on camera. There is a line of work where you let the dimension of the latent space grow when the number of vertices grow. And that gets, so Ed's theorem on the distribution of the leading eigenvectors gets uglier, but I luckily have had people who are smart enough to do that. But here, let's just say the latent position process has a fixed dimension. And it doesn't change on the left here when n increases. So if you just think about your principal component analysis, your eigendecomposition, if you think about Weil's theorem from 1912 or whatever, and as n grows, the non-zero eigenvectors grow order n, and all the ones that are truly zero, the estimate of them are big O of 1. And so as n grows, I can focus in on the dimension, the true dimension, much better. And so on the left, I'm just getting a better and better estimate of the subspace where the signal is. So that's sort of obvious from Weil's theorem, maybe. On the right, though, it's a little bit trickier. As the number of vertices grow, the number of graphs grow, well, if I had a change point and then I had more and more graphs as time goes on, one could hope to, eventually those new graphs are nowhere near the change point, and so how are they going to help you? But this is infill asymptotics, and so I'm getting a finer and finer observation, and so I should be able to, but this is no longer the eigensubspace of the individual spectral graph embeddings. This has to do with the the second turtle, maybe the third turtle, which is the multidimensional scaling, the low-rank representation of the distance matrix. And as m gets bigger there in infill asymptotics, those eigenvectors also concentrate. And so it's two different versions of eigenvectors concentrate, the one on the left and the one on the right. I don't know if it was even related to your question, but I love to say eigenvectors concentrate. I mean, think about it. You walk down the street, and if somebody asks you a question, you just say eigenvectors concentrate.
Thank you, Carey.
Good? Can I come off the stage?
Let's thank Carey again.